Hey there and welcome back. So we talked about the array list in the previous video and we had a small example how it works in Java. We can see the time complexities and how it works with a for each loop and the indexing. And let's talk about the linked list now, because the linked list can do pretty much the same as the array list. But it is kind of special because it implements both the list interface and also the Deques interface. So you can use the linked list for implementing a list, just like the array list, and also implementing a queue or a Deques. If we look at an array list and also the linked list, we can see that first off, the linked list in Java is implemented as a double linked list, and that means that each node has a pointer that goes both ways. So it's not a single linked list, we can traverse this linked list in both directions. So we have a pointer from each node to the other. Okay, and the array list works so that it underneath has an array and it uses indexes, but it also has the consequence that when we need to remove an element or add an element, then we might have to shift some of the elements to the left if we are removing index 3, for instance. So there is some work associated with adding a new element or removing an element. So that's also why we have this time complexity of big O of n when we add an element at a certain index, because we might have to shift these other elements. But a linked list works differently because we don't have an underlying array. We just have these nodes that are connected by references to each other. So if we should make an example first off, let's just see if we make some space here. Let's make a linked list, and let's call this linked cars equals new linked list. And let's just do this in generic way, so we can do car here. So we have a linked list that contains cars at the moment, and we can write linked cars, and then we can write add, and we can see we have a lot of methods in this data structure, many different methods. And the reason why that is because if we go back, the linked list will implement the list interface and also the Deques. So this means that if you search on the internet for the list interface, you can see this will extend the collection interface, has many different methods in this interface, and the Deques, the linked list, will also implement the Deques interface. So we have all these Deques methods. Add first, remove first, a lot of different methods. That is also part of the data structure. So we can see that that's why we have add last, add first. We also have remove first, last. A lot of handy methods. So it's a really versatile data structure, this one. So if we start by adding our C1 here, and let's just copy this code here, because it works a lot the same way. We can add it here, and if we hover over the add method, it will say to us that appends the specified element to the end of this list. This method is equivalent to add last. Okay, so we are adding a new node and connecting a pointer to that. So we can see here that if we want to traverse it, we can make for each loop again, linked cars. We can do a system.println, and let's just see if we have, yes. And also let's have a look if we want to linked cars. Because it also implements the list interface, we can also do the get at a certain index. We can also do get the car at index 1 here. So if we run this code, so we can see that we get, yeah, it's kind of double, because we get all the cars in the list. We also get number 1 index, so that is per show here. That's number 1 index. So it works the same way as an array list, but there are some differences in terms of the time complexity here, because let's just write this up here, because let's make this a little prettier here. So if we look at the array list, we had when we add an element to the end of the list, this can be done in constant time because we're just adding a new node to the end of the list here. So we add a new node, connect a pointer to that, or a reference. So that is in constant time here. If we want to add a new node at a certain index, this is kind of tricky, because if let's assume that we are at the correct element, then we don't need to shift like we did with the array list. We don't need to shift the element that comes after to make room for that, because we just have the pointers. We don't have this underlying array. So this single operation about making the node and connecting the pointers will also be big O of 1, because we're just making a node and connecting the pointers. But and there will be some different opinions about this when you read about the time complexity for adding a new element at a certain index, because we also need to find the correct spot in our linked list to do that. So if I want to insert a new element at, let's just say after number 2 here, then I need to go through the list. I need to go through number 0, 1, 2, and then I have to make a new node and create pointers, adjust the pointers, and that's it. But in worst case, if I want to do this in the end of the list, I have to go through all the linked list. So this could be big O of n to actually find the spot. So, or maybe let's just see here, find correct node. This could be, let's just write this a little bit better here, and then insert node. Okay, so if we combine these two, that we need to find the correct node, we need to traverse the linked list. This is worst case big O of n, almost, and we also need to insert the node. That is a constant time, because we just need to create a node and connect the pointers to that. So overall, this will be big O of n worst case. If we need to go to the end, this node that are just before the end of the list, because we need to traverse through this. We don't have an exact index we can go through. Okay, so if we want to get an index, the array list was really fast at this because we had this underlying array. But the linked list, again, we need to traverse the linked list to find an element, because we don't really have this underlying array. So we need to traverse it, and that could be big O of n in worst case before we find the element. If we want to remove an object or a node at a specific index, this is also big O of n, because if we want to remove element 3 here, then we need to go through this until we find it. And then we have to adjust the pointers. So again, we have to do this traversal. So we can see that if we are adding an element, of course it is still faster just to traverse it and add a new element than shifting all the objects to the left or to the right. So the linked list will be a little bit faster regarding add and remove at a certain index, but then it will be slower when we are retrieving a specific element, because we can see from the array list here that the array list is able to get an object at a certain index in constant time due to the underlying array. Okay, but otherwise it works pretty much the same way, and we can iterate through it. We can also see that we have the iterator as well, we have the size as well, many handy methods to this really versatile data structure. All right, so that's all about the linked list that we can also use as a data structure in Java. Okay, so I hope you make this work and have fun with this. Bye bye.